Welcome back for the second video to lesson 4.1. We're now going to talk about the probability of any outcome is the long-term relative frequency of that outcome. There's three types of probability that we're going to learn about. One is called the classical probability. This is based on equally likely outcomes. Examples for this would be rolling a fair die, drawing cards from a deck, or flipping a coin. Now, when we say classical and equally likely, we mean here, equally likely means that each outcome of an experiment occurs with equal probability. So drawing a card from a deck has equally likely outcomes. However, if we looked at what is the probability of getting all red, so when you're looking at those particular types of questions, sometimes those probabilities are not equally likely, but each card individually is equally likely. That's why we call it classical. Flipping a coin is also a type of classical probability. The second type of probability is empirical probability. It's based on real life experiments. For instance, blood type, whether a student will travel by plane over Thanksgiving, the number of students that are happy with the classes that they take, those are based on real life experiments. The third type of probability is based on opinion. And my big example here is the Lions are going to win the Super Bowl. So this year it's going to be for real. Okay, let's look at an example. Classify each statement as an example of classical probability, empirical probability, or subjective probability. A says the probability of getting 3 clubs when being dealt a 5-card hand. This would be considered classical probability. They're based on the idea of equally likely being chosen. B, the probability that a bus will be in an accident on a specific run is about 6%. That is empirical because that data comes from actual outcomes of accidents with buses. C, the probability that a person will watch the World Series is about 0.15. Again, this is empirical. Because it is based on evidence of people that actually watch or don't watch the World Series. They have data collected on that. And D is the probability of winning at a chuck-a-luck game is 5 out of 36. Again, that would be classical because it's based on equally likely outcomes. So how do we calculate probabilities? To calculate the probability of an event A, when all outcomes are in the sample space are equally likely, count the number of outcomes for event A and divide by the total number of outcomes in the sample space. So X is the number of outcomes for event A, and N is the total number of outcomes in the sample space. You can divide X divided by N and record that as a decimal or as a percent as well. So for example, if you toss a fair dime, there are 2 outcomes, heads and tails. H is going to equal heads, T will equal tails. We denote the probability of getting heads as the probability of H for heads equals 1/2. That can also be written as a decimal as 0.5, and it can also be written as a percent as 50%. There are 4 rules to probability that are important. The first one is that the probability of any event E is a number between and including 0 and 1, and it looks like this. So it could be 0, which means it's impossible to occur if we look on the number line here, all the way up through 1, which is it's most certain to occur. Anything that is unlikely to occur is going to be between 0 and 0.5, and anything that is likely to occur is going to be between 50 and 1. The second rule is that the sum of all probabilities must equal 1. The third rule is that if an event E cannot occur, its probability is 0. And number 4 is if an event E is certain to occur, then the probability is 1. Some books or people will say there's 2 rules to probability, and these are the 2 that are important that you should know. Definition of the complement. So the complement of event A is denoted as A prime. Sometimes it's also written as A to the C for complement. Sometimes it's written like we have it here as A with the bar above it to show the complement. But one thing that's important to know is that the probability of A plus the probability of its complement equals 1. Or we can say the probability of E complement is equal to 1 minus the probability of E. Or the probability of E is equal to 1 minus the probability of the complement. And again, the probability of E plus the probability of its complement equals 1. So let's look at a couple examples. Let S be the sample space of 1 through 6, and let A be the sample space of 1 through 4. Then the complement of A is all of S that's not in A, which would be 5 and 6. And the probability of A is 4 out of 6. The probability of the complement of A is 2 out of 6, because that's the numbers 5 and 6. There's 2 out of 6. The probability of A plus A complement are equal to 1. Example 5. A card is drawn at random from a deck. Find the probability of getting these results and use proper symbols. So it says the probability of getting a 6 and a spade. So the probability of a 6 and a spade. Since there's only one card that is a 6 and a spade, we have 1 out of 52 likelihood for that. And that decimal answer is 0.0192. Usually on probability, if the decimal does not terminate at 2, we usually go out to 4 decimal places. What is the probability of a king? So that would be the probability of a king. And there are 4 kings in a deck of 52, so we would write that as 4 out of 52. And that decimal comes out to be 0.0769 or 7.69%. And I did not comment up here. This would be 1.92%. Not a heart. So we could say that this is the probability of a heart complement, or the probability of a heart with the bar above it. And so we can find the probability of not a heart by adding up all the ones that are hearts, or we could say 1 minus the probability of getting a heart. And if we do that, that means we're going to say 1 minus the probability of a heart is there's 13 hearts. So 1 minus that would be 52, subtracting 13 over 52. So that leaves us with 39 out of 52 hearts. That 39 out of 52 cards, apology there, divided by 52. So 39 of the cards are not hearts. And so that would be 0.75 or 75%. And number 4 says a diamond or a heart. So the probability of a diamond or heart. And so that means there are 13 diamonds plus 13 hearts over 52. Gives us 26 over 52, which comes about to be 0.5 or 50%. Next is another representation or picture that we use to help us in probability, and that's called a Venn diagram. A Venn diagram is a picture that represents the outcomes of an experiment. It generally consists of a box that represents the sample space to S together with circles or ovals. The circles or ovals represent events. So this is just an example here. It says, suppose we have an experiment of the outcomes 1 through 12, where each outcome has an equal chance of occurring. And A is the event of 1 through 6. And B is the event of 6, 7, 8, and 9. Then A and B is 6. 6 occurs in both A and B. And A or B is anything in A or B, and that would be 1 through 9. The Venn diagram is as follows. And you can see that 10, 11, and 12 are not in events A or B at all. So let's get practice drawing an event diagram. Example 6 says, suppose an experiment has outcomes black, white, red, orange, yellow, green, blue, and purple, where each outcome has an equal chance of occurring. Let event C be green, blue, and purple, and event P be red, yellow, and blue. Then it says we know that C and P share blue, and C or P contain green, blue, purple, red, and yellow. Draw a Venn diagram representing this situation. I'm going to draw a rectangle big enough to fit all this in. And I'm going to, C is going to represent that event, and then P are my two main events. And I always look for the overlap. So C and P means that blue has to be in both. So blue is going to be in both. I'm going to have the circle for C and the circle for P, and they overlap with blue. So taking care of that. Then in C, we also have green and purple. And then event P, besides blue, we also have red and yellow. And then C or P means it's in any of those: green, purple, blue, red, and yellow. And then we also had black, white, and orange that are not in either of these events. So we can write them anywhere. So black, white, and orange are still in the sample space, but they're not in either of these events, C and P. Let's look at example 7. Roll a pair of 6-sided die. Let A be a prime number of dots is ruled. Let B be an odd number of dots ruled. Let A equal 2, 3, and 5, because they're the prime numbers in 1 through 6. B is an odd number, that would be 1, 3, and 5. Therefore, A and B is 3 and 5, because 3 and 5 occur in both. A or B means any number that happens in A or B, 1, 2, 3, and 5. Draw a Venn diagram for this. Venn diagrams are nice to use sometimes in situations for myself, to where I can kind of draw a picture to the situation. Even if the problem's not asking me to do that, sometimes I use it for my own advantage. So here's my sample space S, and A has 2, 3, and 5. B has 1, 3, and 5. And we said 3 and 5 are shared by both. So I'm going to draw them in the overlap here. 2 is also in A, and then B also contains 1. And then we had 4 and 6 that are not in either of these events. Example 8. 50% of the workers at a factory work a second job. 25% have a spouse who also works. 5% work a second job and have a spouse who also works. Draw a Venn diagram showing the relationships. Let W be they work a second job, and S equal to spouse also works. Okay, so this is one where we have to kind of think about the situation and draw a picture to it. So here's my overall sample space. And then I've got W is they work a second job. And the key here is 5% work a second job and have a spouse. So 5% of my people do both. So I'm going to keep that together here. And so it says 25% have a spouse who also works. Okay, so that would be 25% have a spouse that also works. Well, if 5% of them are in the overlap, then we know that 25 minus 20, 25 minus 5 is 20. So that would be my total of 25% of that also have a spouse that works. They also told us up here 50% of the workers at a factory work a second job. Well, we know 5% of them do both. So that means 50 minus 5 equals 45%. Have just a spouse they work a second job. They also have a spouse that works. And then we have, so if we have here 45 plus 5 is 50, plus 20 is 70%. That means we have 100 minus 70% or 30% of workers that don't either have a second job or have a spouse that works. It's just them. So they have to be accounted for out here. Lastly, in this end of lesson 4.1 video, I wanted to talk about two last topics. One is the law of large numbers. It is a theorem that describes the result of performing the same experiment a large number of times. According to the law, the average of the results obtained from a large number of trials should be close to the expected value and tends to become closer to the expected value as more trials are performed. So if I were to sit here and flip a coin, I could get 80% of the time I might get a heads. But if I were to flip a coin over and over again for 100 or 200 or 300 or 400 times, more than likely I'm going to keep getting closer and closer to 1/2, because that would be my classical probability of the probability of getting a heads should be 1/2 and the probability of getting tails should be 1/2. Also, probability and risk taking. We are taking risks every day. Some of them are riding in the car, going on a plane, eating food produced in a factory, right? We don't know about the cleanliness. Investing in the stock market, that's taking a risk. Some risks are lower than others and some are higher. Depending on what we wear, people might make fun of us, right? So they're choices and assessments that we have to make. But that's something that is also always taken into account and thinking about when we're talking about probability. So catch me back for lesson 4.2. We're going to dive into some more theories and formulas in probability.